Okay, so this was discovered, or a way of overcoming these restrictions was by Bohr. And Bohr's model is called the planetary model. And Bohr's model was ingenious because it not only solved the problems with Rutherford's model, but it also was able to align with other research being done and make several predictions. Now, Rutherford worked with the cathode ray tubes again, but with his cathode ray tubes, he filled them with hydrogen gas, and he applied different amounts of radiation, of electricity to them. The reason was he wanted to generate spectrum. So remember when we were talking about light that comes from a star, especially a star like ours, where if I were to pass that light through a spectrum, I'd have all the colors of the rainbow. And we call this our continuous spectrum. Well, what was known is that if I take a sample of hydrogen gas and I seal it in a container and I pass really high energy electricity through it, it produces a light. And if I take this light and I pass it through a spectrum, I get these individual lines. And so what Bohr did was he set out to explain why hydrogen produced these lines of different color when I passed electricity through it. Okay, so he proposed a mathematical model to explain this. And the key thing that he did, which helped to solve a major problem in Rutherford's model, was that he said that each electron had a certain amount of energy, which he called a quantum of energy, which allowed it to maintain its position around an atom. And so this answered the question as to why don't electrons fall into the nucleus. Electrons don't fall into the nucleus because they have a certain amount of energy that allows them to maintain their position. Just like why don't planets fall into the sun when they're going around? They don't fall into the sun because they have a certain amount of energy due to their movement around the sun. Bohr said that electrons orbit the atom much like the planets orbit the sun. Okay? Electrons have a given amount of energy, a quantum of energy, which allows them to stay in their position in their orbit. The further from the nucleus an electron is, the greater its energy. Okay, so electrons in an orbit 3 distances away has more energy than an electron in the first orbit. Each orbit can only hold a specific number of electrons. So the first orbit can hold 2 electrons. The second and third orbits can hold 8 electrons each. And finally, he said electrons cannot exist between orbits, but can move from one orbit to another. So much like we have our planets, the planet Earth and Mars, we don't have a planet in between Earth and Mars. Okay. But electrons can, unlike the planets, electrons can move between orbits. So if I have an electron in orbit close to the nucleus, I can have it move further away if it's gained energy. And we say that it's become excited. If I have an electron that's excited and it's further away from the nucleus than it should be, it can move back to its original position, and when it does, it releases energy in the form of light. And this is where Bohr's line spectrums came from. He said that if I take an atom and I excite the electrons, move them further away, and then let them fall back, they release light. So let's take a look at his model and what this means. So here is an example of his model, and we have to remember Bohr's model, when he was just deriving it in 1910, 1915, we didn't know about the nucleus yet, the neutron yet, but we knew about our positive nucleus, and we had our electrons around. So here's my nucleus with my proton in center. Here's my electron in my first orbit. Hydrogen only has 1 proton and 1 electron, so that's all I have. My second orbit and third orbit don't have electrons because hydrogen doesn't have any electrons to place in them. But if I take this electron and I give it some energy, so let's say I pass a high energy current through it, this electron is going to become excited and move to a higher orbit. And it could move to that higher orbit because it was empty and there was space for it to move to. Now this electron, it doesn't want to stay up here, it's unstable, and so therefore it's going to want to lose the energy that it's gained, and it's going to fall back to its original position And when it does, it's going to give off light. And this is the light that Bohr then took and passed through his prism to get his line spectrum for hydrogen. Now, Bohr's model was really good because it did a number of things. First of all, it solved the problem with the previous model. It didn't throw out the previous model. It made improvements. And this is often what happens in science, is that we get incremental changes to models till we get to what we had. More importantly, it helped to explain research done by other scientists around the time, especially Planck. Planck and Einstein were the ones who came up with the concept of quantum by working with other things and what happens when we heat solids. Okay? It allowed for us to explain and predict the spectrum of hydrogen. It provided insights for future studies. So this is a really good model. Okay? Now, Bohr's model wasn't perfect. There are problems with it. And as a result, in the 1920s, we ended up with our quantum model, but we're not going to talk about this. This is going to be saved for grade 12. Okay? His model combined both scientific models that showed the electron of the subatomic particle. So there are a number of scientists that were doing work that showed the position of scientific subatomic particles using both light and electricity. And he was able to do that. More importantly, his model provided us a tool to predict the chemical and physical properties of an atom and to explain some of them. We can use this to explain what happens when a lithium atom reacts with a chlorine atom, because his model allows us to explain the chemistry.